Okay, so we did one example. We stopped short of kind of like representing these things as functions themselves, but hopefully you can see that we would be able to kind of like write a like succinct series using the pattern that we see here. But what we're going to do is we're going to go ahead and jump to a new example because I want to be able to show you the setup for these problems at least 2 times. And then as we get more comfortable with these ideas, we can start to think more deeply about what the final solution looks like. So this is going to be example 5.1.4. We're looking at the differential equation y double prime minus 1 plus x y equal to 0. And so using the same reasoning as before, if our ordinary point is x0 equal to 0, sort of we see that our p of x is 0. There's no y prime term. And our q of x is 1 plus x. So we're going to have a radius of convergence that's infinite again. Sorry to breeze right through that, but this problem is going to be long, and already the videos for this section are very long. So we're going to go right to plugging stuff in to, we're going to plug y equal to the sum from n equals 0 to infinity, cn x to the n, and derivatives into our ODE. You know, I write derivatives so often, but every once in a while I just forget how to spell it. So 0 equal to y double prime minus 1 plus x times y, when we use our series, are going to be the sum from n equals 2 to infinity, cn times n plus 1 times n times x to the n, oops, sorry, I'm orienting myself the wrong way, cn times n minus 1, x to the n minus 2, minus 1 plus x, the sum from n equals 0 to infinity, cn x to the n. We can go ahead and use algebra to distribute the sum across that minus 1 plus x. So that's going to give us the sum n equals 2 to infinity is unchanged, cn n minus 1, x to the n minus 2, minus 1 times the sum from n equals 0 to infinity, cn x to the n, minus x times that sum. So the sum is still going to go from 0 to infinity, still going to have cn, but now x times x to the n gives us x to the n plus 1. And then next, what we're going to do is we're going to try and match the powers up. So we want to take xn plus 1 and xn minus 2, and let's have them meet somewhere kind of like the middle at xn. So actually, I'll leave those circles there to kind of indicate what I'm thinking about doing. So we'll say distribute, match powers. Just quick notes on the side to kind of tell us what I'm trying to do here. So if I want to bring this term down to xn from n minus 2, let's do this one the sum way, and then we'll do the other one the thinking through the steps way. So n minus 2 to n means adding 2. So this is going to give me cn plus 2 times n plus 2 times n minus 1 plus 2 would give me n plus 1. The sum doesn't follow that rule, it does the opposite. So n equals 2, subtract 2 takes me down to n equals 0, to infinity. And we can check real quick that this makes sense. So originally, our first term would be x to the 2 minus 2 is 0, times 2 minus 1 is 1, times 2, times c sub 2. That's our first term when we plug in n equals 2. Now our first term is when we plug in n equals 0. So that's going to give us x to the 0 times 0 plus 1 is 1, times 0 plus 2 is 2, times c to the 0 plus 2 is c sub 2. So that adding what's inside the sum and subtracting the index on the sum rule does work if that's the way you prefer to remember this. The middle term is already at x to the nth power, so we'll leave it. For this one, we'll go ahead and follow through reasoning how we move from n plus 1 to n using the lowest bound, if that's the way you prefer to think about it. So the first term before, when we plugged in n equals 0, would have been c0. X to the 0 plus 1 is 1. Now we want to start from xn. So if I want that to be x1 for my first term, I'd better start from n equals 1. My first term should be at c0 when I plug in n equals 1, so that must be n minus 1. 1 minus 1 would give me c0. That's going to check out as well. Either approach you want to take is fine, whatever makes more sense. I think reasoning through this step using the power makes more sense, but probably filling in this step using the sums makes more sense. But you might feel differently. Okay, so next up we have 3 sums, and some of them start in the same place, but some of them don't. So we need to make sure that they all have the same first index. And you could move this one down to 0, but for me, it's always easiest to move things upwards. So I'm going to go ahead and do that. If you wanted to do otherwise, you could, and it would still work out in the end. But I'm going to say I want this one to start from 1. Everything can stay the same inside, but I just have to take care of my 0th term out front. So my first term would have been c2 times 2 times 1, x to the 0, plus everything else. And then I'm going to do the same to this sum right here. So I want it to start from 1. And I just have to take care of my 0th term. That one would be c0 x to the 0 out front. And then this one already starts at n equals 1, so I can go ahead and keep it the same. So all I did in that step was I made sure to match the lower index. And then I can go ahead and combine my series now. So out front I've got 2c2 minus c0. Let me underline those some way so that you can see what's happening. And then inside the sum, I start from 1 and go to infinity. And everything multiplies by x to the n. And what I have is, now I'll start by writing it out and then I'll underline so you can see how they're similar. Cn plus 2 times n plus 2 times n plus 1 minus Cn minus 1. And where those came from is, here's my first term. What's the line I haven't used yet? Oh, regular underline I haven't used yet. There's my second term. Remember there was a minus sign out front, so I distribute it over. And then here is my last term, right there. So this sort of mistake where the minus sign doesn't get distributed is really common in this section. You know, it'd be very easy to just have said, oh, there's a Cn, I add Cn. Just be careful, watch your algebra. I know it's easy to make mistakes, and I don't personally care if you make small algebra mistakes as long as you're following the process, but if you make small mistakes that get your relationships wrong at this stage, it makes the next stage harder. So next up is going to be finding those coefficients so that this is equal to 0. I'm going to write those right now, and then we'll continue actually finding those relationships in the next video. So we've got 0 is equal to 2c2 minus c0 is our first, and n plus 2, n plus 1. Minus Cn minus Cn minus 1. So we'll plug those into our coefficients in the next video and wrap up this section.